Welcome to our journey for differentiation and integration. We will now leave back prop bay and come to a crossroads. We'll take the left-hand path down the crossroads to look at forward-backward beach. In this lecture, we will look at the forward-backward algorithm. The key idea we'll see today is to use automatic differentiation to derive the forward-backward algorithm. And this is, of course, related to different algorithms such as dynamic programming, message passing, belief propagation, and inside-outside. So consider a hidden Markov model with 4 hidden nodes and 4 observed nodes, as shown by the directed graphical model in the middle of the slide. So we denote the hidden nodes by the variables z1 to z4, and we denote the observed nodes by variables x1 to x4. Given a hidden Markov model, there are several different probabilistic inference questions we could ask. For example, we might want to find new observations. For example, we might want to generate new observations for given hidden states. Or we could estimate the most likely hidden states given the observations. Or we could estimate marginal distributions, or even learn the parameters of the hidden Markov model. Here, we focus on computing the distribution of the hidden state variables given the observed variables. And we do this by a well-known algorithm called the forward-backward algorithm. For an introduction to hidden Markov model, I refer you to the tutorial by Rabiner in 1989. And for further details, the book cited here. Hidden Markov models are part of a bigger class of algorithms called dynamic programming, and was invented by Richard Bellman of the famous Bellman equations. You can think of what we're presenting today as an automatic differentiation method applied to arithmetic circuits. This has already been proposed by Adnan Dawicha in 2003, and more recently there was a tutorial in an LP venue by Jason Eisner. Recently, Tom Minka gave a talk which looked at the connections between hidden Markov models and more generally Bayesian networks, and how automatic differentiation can be thought of as message passing and belief propagation. So recall that automatic differentiation is like the chain rule, except we cache intermediate results. And for this lecture, we focus on the circuits which only involve addition and multiplication. The key idea is that the gradient of a multiplication scales with the value of the other input. So, for example, we're given an equation E is A times B. We observe that the gradient of E with respect to A is B, and the gradient of E with respect to B is A. Here is a computational graph. This graph is deliberately organized such that it flows from right to left. So we start from the right-hand side and look at the variables A and B, and we have an intermediate variable E, which is the multiplication of A and B, and E and F are summed together to construct G. Let's see what happens when we apply reverse mode automatic differentiation to such a graph. If we look at the gradient of G with respect to A and B, we get the following result by the chain rule, namely that we can chain together the gradient of DG DE and DE DA, and correspondingly for B as well. By substituting the gradient for the product E equals AB, we can see that actually DEDA is actually B, so we can simplify that first expression, and DEDB is A, so we get that second expression. The key variable here in this graph is the middle variable E, which allows us to do that substitution. Recall that we had this idea of the dual number, We can think of differentiation with respect to an intermediate variable as a function. You think of the operation d by dE as an operation on the variable g. So the equations on the previous slide can be thought of as the partial derivative with respect to A, and the partial is equal to the partial derivative with respect to E multiplied by B. Automatic differentiation augments each variable, for example, a variable A, with the adjoint variable, which we denote by A with a left pointing arrow, and this finds the adjoint pair. The adjoint of A is the function that takes a partial differential d dA. So given this representation of the adjoint of A as the partial differential d dA, we can write the equations from the previous page as follows. Given that we have an equation such as E equals A and B, we can obtain a pair of adjoint equations. Adjoint A equals adjoint E times B, and adjoint B equals A times adjoint E. And this pattern is repeating. Recall that A is the input and E is the output in this particular equation. By looking at the adjoint equations, you can see that the input adjoint is the output adjoint multiplied by the partial differential. And in this particular case, for multiplication, the partial differential turns out to be the value of the other input. Okay? So this result here generalizes to a product of n variables generating n corresponding adjoint equations. This is special for multiplication. So let's go back to hidden Markov model. We can derive the backwards pass by considering the trellis, and we can obtain the forward pass by essentially doing reverse mode of automatic differentiation. So the reason we presented the computational graph earlier, going from right to left, is so that it corresponds to going backwards in the hidden Markov model. So recall the same model here. We have 4 hidden nodes and 4 observed nodes, and we focus on the recursive part of the flow of information from right to left, in particular going from node Z3 to Z2. If we look at that flow of information from Z2 to Z2, we see that we can write down the following messages for Z3. Okay? We assume that each hidden node has 2 possible states, A and B, and denote the message originating at Z3 going left as the vector beta, as you can see by the vector here. To compute the corresponding message at Z2, we have the following recursion, which is essentially the message at Z3 updated by the transition from Z2 to Z3. Remember, this is going right to left. So this transition also includes the emission of symbol x2. So normally when we implement hidden Markov models, this function g here is decomposed into the transition probability from Z2 to Z3 and the emission probability from Z2 to x2. Okay? But here we just pack them together to simplify the notation. Okay? And again, the functions g here denote the transition from Z2 to Z3. If you look carefully at the equations here, you will note that there are 6 input nodes on the right-hand side. So there's 4 values of g corresponding to the 2 nodes Z3 and Z2 and the 2 possible states A and B. But there's the same 2 nodes for beta, which is only Z3A and Z3B are there. Now, by collecting these nodes and carefully looking at how the messages are passed from right to left, you will get the following computational graph on the left-hand side. Okay? This computational graph is slightly different from the computational graph on the right. The key differences are the fact that the betas are shared between the two parts of the computational graph. Right? It's essentially two copies of the computational graph we've seen before, except now the two copies have the same input, which is the beta of Z3A and the beta of Z3B. Okay? And by mechanically doing automatic differentiation, namely reverse mode automatic differentiation, we can derive the forward pass of the algorithm from the backward pass algorithm. And this is what has been done by Jason Eisner in this algorithm here. Now, the thing to note here is that in that paper, they derive it for more general cases, such as probabilistic context-free grammars as well. So this approach works more generally than just for forward-backward. If we look at the following computational graph, x and y, that goes to z, we can compute the forward pass by essentially implementing the chain rule. And the reverse pass, as you can see here, implements the rule that the input adjoint is the output adjoint multiplied by the partial differential. Okay? This pattern is quite general and can be used to derive all sorts of interesting message passing algorithms. In summary, we consider a special case of addition and multiplication computation. This allows us to look at the special case when the adjoint patterns have a nice form. It's worth recalling that hidden Markov models are a special case of more general dynamic programming. And we have seen today that given the backward algorithm, we can derive the forward algorithm by reverse mode automatic differentiation. In summary, backpropagation is just simplified message passing in probabilistic graphical models. Thank you.